Okay, so that's our first classifier. It's still used quite a bit. It's not a bad classifier to try out as your first option. We saw with the digits that with nearest neighbors we already were predicting with 97% accuracy. So it's certainly, as simple as it is, it's definitely not something to just disregard. But now let's look at some other classifiers. And specifically, let's start by thinking statistically. So how can we measure the quality of a classifier? So for any classifier, we really care about two sides of the same coin. We care about the prediction accuracy, which is the probability that our classifier is going to be right. So what's the probability that we have a classifier that is going to predict the correct label for X? Similarly, we could care about the prediction error. So we want to maximize the prediction accuracy. The prediction error is just the probability that we get it wrong. And so we want to minimize that. But before we can calculate these probabilities, we're making a statistical assumption. So we're going to assume that there's some distribution P underlying our data set. And what this means is that the labeled examples that are coming to us under our assumption are going to be IID, independent and identically distributed according to some underlying ground truth distribution that nature provides, but we don't necessarily get to see. So for example, when the next email comes to us, or when we get the next email in our data set, we're going to assume that that's just coming totally at random, and the label of whether it's in spam or not is also totally at random according to some joint distribution on both the email and the label combined. So there's a joint distribution now on both the covariates X and the label Y. So why do we make this assumption? So a similar question is to ask, when is there any hope for finding an accurate classifier? Why do we think that we should be able to predict spam emails and distinguish spam emails from non-spam emails with any accuracy? And so the key assumption is that by assuming that our labeled data in our training set are coming to us IID according to some ground truth distribution, and also that all future data that's going to come to us is generated according to that same distribution, with the exception that with our training set we get to observe Y, whereas with our testing set we only get to observe X, we can take advantage of the statistical regularities there to assume that things that perform well on our training set are going to generalize well to our testing set. So this is the flowchart of that. So past labeled examples from P come in IID. We pass that to some learning algorithm. Then some new unlabeled example comes to us according to the same exact distribution. And by then predicting the label, because we have the same distribution assumptions here and here, what we learn on from this data set will generalize well to this data set. So there's an entire theory that formalizes this, statistical learning theory or theoretical computer science. Those two areas would formalize this. We're simply going to make this claim that by assuming that our data is coming to us IID, what we learn on based on the past will generalize well to the future. And even though we didn't discuss this for regression, it's important to say that actually regression is also making the same assumptions.